Hi everyone! You've made it through hypothesis testing, at least for 1 and 2 means. But what happens if you want to test more than 2 means? Well, you could sit there all day and do hypothesis tests on each pair of means and then get your answer from all that information, or you could just run Anova. Anova compares 2 or more means together and says, all right, is there a significant difference among these means somewhere? Note that Anova does not tell you which means are different. They just tell you there is a difference. So if you have 6 means, for example, from 6 different experiments, and you run them through Anova, Anova is not going to tell you which one or which ones are different. You're going to have to do a post hoc Anova test to do that. But Anova will tell you, hey, you got a difference here, you need to check it out further. So in this course, we're going to go through Anova tables. I do not expect you to calculate sum of squares for that table. That will always be provided to you, or you'll be able to figure it out from the table data. You do not have to go through those big long formulas that you may remember from stats for calculating sum of squares. Those are a pain. And I don't want you to get bogged down in the math when what I'm really concerned about is, can you interpret that Anova table? The reason for this is that you have tons of statistical software that can do that math for you. But when you get that printout from any kind of analysis, you need to be able to look at those tables and understand, did my data actually go through this thing correctly? Did it pick up all my treatments? Did it consider what I consider to be a treatment? Did it get all of my treatments? So when you're looking at that table, you can say, aha, this ran right, and so these are my actual results, or, oh no, wait, it skipped this thing. I need to go back and rerun this and make sure I'm telling it to pick up the right thing this time. One of the hardest parts of these tables is figuring out your degrees of freedom, and this comes from the number of levels in each treatment and the number of replicates you have in your study. So here I'm going to go through filling out the degrees of freedom with you for these tables, because again, this is really what commonly trips people up. Once you have your sum of squares, your degrees of freedom, you can pretty much just crunch through everything else, no problem. But getting those degrees of freedom, that's the bit of a tricky part. So let's take a look at a couple of Anova tables. Here is a very simple one-factor Anova. Now here our factor is A. A can be whatever you want it to be. It can be temperature, time, sugar level, salt level, acid concentration, whatever you want. It's just our particular variable. We have one variable for this study that we are looking at. Sum of squares is where all that information from your averages come in. We won't deal with that right now. What I want to go through is degrees of freedom. So let's see how to do that. With degrees of freedom, you have basically for A, the number of levels of A, here we've got 4 minus 1. So we're going to have 3 degrees of freedom for that. And if you're thinking, well, wait a minute, why do I have 3 degrees of freedom? Because I had 4 levels in my particular little variable here. That is because if you're thinking about testing them in a certain order, you can put them in whatever order you want except for the last one you pick. It has to go there. There is no other space for it to go. That means you can put 3 of them in any spot you want, and then the 4th one has to go in the remaining spot. So that's why you have 1 minus for your degrees of freedom. For your error for a single factor Anova, that is small a, which is the number of treatments in A, so here we've got 4, multiplied by the quantity of little n minus 1, where little n here is your number of replicates per treatment, and that's 2. So here we have 4 times quantity 2 minus 1, or 4 times 1, which is 4. And our total degrees of freedom, well, that's easy. We just add up everything in the degrees of freedom column, and we get our total. So that's 7. And we can double check that we did our math right, because you can also calculate the total degrees of freedom by multiplying little a times little n. So little a here is 4, little n is 2. So that's 8. When you subtract 1, you get the total degrees of freedom, which is 7. That checks out with what we have. We are good to go for this table. Now let's see what happens if we have a table where we have some of the degrees of freedom information, we have some of the sums of squared, some of the mean squared, but we have absolutely no information about what happened in terms of number of treatments, replicates, number of levels of a particular variable. How do we figure this out? Well, let's start with the easiest bit we have right here, which is our variable a. Here we've got sum of squares and we've got mean squares. So mean squares is calculated by taking the sum of squares and dividing it by degrees of freedom. So that means if we reverse where everything is, if you take the sum of squares and divide by the mean squares, you're going to get the degrees of freedom back out. So that's 6. Now we're going to say, okay, well, we've got 17 total degrees of freedom, and we know everything in that column adds up to our total degrees of freedom, which must mean that our error degrees of freedom are the total minus a, and so that would be 11. And from here we can go on to figure out the rest of our table, our mean squares, and our f value. We have all our degrees of freedom and we are all set to do that. Now let's take a look at a two-factor Anova table. Here a and b are our two variables, and we also have an interaction, ab. We have error again, we have total again. So this means we're going to have 5 entries in our degrees of freedom column. Let's take a look at how to do this. Well, you calculate your single variable degrees of freedom exactly like you did in a single factor Anova table. So our degrees of freedom for a is little a minus 1, that is 4 minus 1, and that's 3. For degrees of freedom for b, that is little b minus 1, so 3 minus 1, which is 2. ab is the quantity, little a minus 1 times the quantity, little b minus 1. So basically you can just multiply your degrees of freedom for a and b times each other and get ab, and that would be 6. Your error. There's 2 different ways to do this. You can figure out your total if you have totally forgotten the error formula and just subtract everything else out. You get your error degrees of freedom. That works too. Or you can use the formula a times b times the quantity n minus 1. Here n is 2, and that's little n. So we have 4 times 3 times the quantity 2 minus 1, or 4 times 3 times 1, which is 12. And if we add up all our degrees of freedom here, we have 3 plus 2, which is 5, plus 6, which is 11, plus 12, which is 23. And we can back check that by doing our formula for our total, which is little a times little b times little n, all of that, minus 1. So if we have 4 times 3 times 2, that is 24, minus 1 is 23, and we have filled out this table correctly. Okay, let's go. Okay, let's go to a partially filled out table. Figure out our degrees of freedom from this. Well, we'll start with A. We can figure out our degrees of freedom. That is 3. Same thing with B. That is 4. And here I'm using the same rules as I did in that single factor Anova table where I'm taking the sum of squares and dividing by the mean square. I don't have any information on AB, but I do have the degrees of freedom for A and B. What I can do is just multiply them together, and I have AB. And since I was given the error degrees of freedom, I can add everything up and get my total degrees of freedom. So we have 3 and 4 is 7, plus 12 is 19, plus 40 is 59. And there's that Anova table. Okay, now that we've gone through how to fill out one factor and two factor tables, let's give you guys a little bit of practice. So take a look at this particular table. Pause the video for a second and see if you can fill in the degrees of freedom column. And there's the completed column. Check your work and see if you got it right. If not, go back and try again, fix what errors you had. When you're done with that, let's try a two-factor table. So pause the video for a second, see if you can fill in that degrees of freedom column. How about this time? Did you get this one? If not, that's okay. Two-factor ones are often trickier than the one-factor simply because you just have more things to take care of in this column. So if you didn't get everything right, go back, see where you made mistakes, and correct them. If you got everything right, awesome, great job. The last thing I want to talk about in this video is figuring out how many replicates you have for each treatment, or each combination of A and B and a two-factor, or each level of A for a one-factor. You can actually back this out from the degrees of freedom information. So let's go back to this one-factor table here because it's a bit easier with one factor. Remember, the formula for error is A times n minus 1, where this is little a. All right, well, we know from our degrees of freedom that this is little a minus 1, so a must be 3 here. And so if we take our total degrees of freedom and divide it by a, we're going to get n minus 1. So that would mean n minus 1 is equal to 1. So if we scoot that minus 1 to the other side, we get n, which is 2. And that means we've got 2 replicates for each level of A here. And if you think about it, if we've got 3 levels of A and 2 replicates for each level, well then 2 times 3 is 6, and then minus 1 should give us our total degrees of freedom, and it does, it's 5. So that's how you back out little n from degrees of freedom for a single factor ANOVA. But how about for a two-factor? Well, the formula for this is A, B times n minus 1 for our error. Now, we know our error is 24. We know A from the degrees of freedom has to be 2 because that's little a minus 1. So little a is 2. B for our degrees of freedom, that's little b minus 1, so little b has to be 4. And so if we take 24, divide by little a and little b, so we're dividing by 2 times 4, which is 8. N minus 1 is 3. And so that means n is 4. We have 4 replicates per treatment here. Let's double check with the total. So if A is 2, B is 4, and N is 4, 2 times 4 times 4 is 32, minus 1 for our total degrees of freedom is 31, and that matches exactly what we have here. So we got N right. It is equal to 4. And there you have it. That's Anova Tables. That's how to fill out your degrees of freedom. As always, any questions, feel free to contact me.